Here we're continuing exercise 17.7, which is asking us both to predict the products of these reactions and also to propose a mechanism for how they happen. And it's HX addition, so hydrohalogen addition to a conjugated pi system is what we're doing. So in these cases, the two pi bonds in the diene act as a each could act as a nucleophile. Now, this molecule is not symmetrical, and so we have to think about two cases. We have to think about one case in which the pi bond on the left is the one that attacks the slightly positive hydrogen. The bromine there is pretty electronegative, so it steals the electrons for itself, and the hydrogen it's bonded to loses those, so it becomes slightly positive. So either the pi electron on the left that doesn't have that methyl group attached to it could attack the hydrogen electrophile, or the pi bond on the right could do that. So we have to think about both of those two cases. Let's start with the one on the left first. So if this pi bond attacks the electrophile, hydrogen can only form one bond, so the bond that it has breaks. Those electrons are going to go onto that bromine. The bromine already has 3 lone pairs on it, so it's just going to get that extra 4th lone pair from the electrons in the bond. And the result of this, the product you get at first, let me put that underneath. The product you get at first from this is the hydrogen adding right here. And the reason for that is that if the hydrogen adds there, then the carbocation you form is allylic. It's one atom away from an atom in a double bond, and so it's stabilized through resonance. So that's the most stable carbocation you could form, and so that's the one you do form. But you do have resonance, so you want to warn the world that the structures you're drawing, those resonance structures, are not the true structure. The true structure is the one that you get when you take the average of the structures inside those brackets. And that's what that double-headed arrow is telling you. It's telling you neither of the structures on either side of this are true. None of those structures ever exist. The only structure that ever exists is the average of these two. Now, when you have an allylic lone pair to draw the other resonance structure, all you do is you take that pi bond and move it toward the positive charge. So then that pi bond goes away, it moves, and the allylic and the positive charge moves to the carbon that just lost electrons. So those are our two possible carbocations, the two places where there are slight positive charge. And after that first step, the bromine, when the bromine left, it gains those electrons in that bond and has now a full negative charge. So it's a strong nucleophile. And as a nucleophile, it can attack 2 places. It can attack the positive charge represented in that resonance structure on the on the left, in which case you would get this product or it could attack the positive charge that's represented in the other resonance structure, in which case you'd get this product on the right. And if you're just trying to classify those two products, you can see on this one on the left, the hydrogen and the bromine attached to carbons 1 and 2, so that's called the 1,2 product. And for the one on the right, the hydrogen and the bromine attached to carbons 1 and 4, so that's called the 1,4 product. So those are the products you'd get if this pi bond on the left, it acts as the nucleophile. But of course, in a population of hundreds of trillions of these molecules, sometimes the other pi bond will be the one that acts as the nucleophile. So let's think about the products that we'd make when that acts as the nucleophile. So that attacks the electrophilic hydrogen. That hydrogen can only form one bond, so if it's forming this new bond, the bond that it has, the electrons break. They go to the most electronegative thing nearby, which is the bromine. And then we end up getting the hydrogen adding at the top of that double bond. So the hydrogen adds up here. And that's because that leaves you with an allylic carbocation. So this carbocation is going to be stabilized through resonance. So it's the most stable carbocation, that's the one that forms. Because we do have resonance, we have to warn people the structures that we're drawing here are not the true structure. The true structure is only the average of these. So you draw that special resonance arrow that means take the average. Neither of the true structures on either side of this arrow ever exists. Only the average ever exists. So when we want to draw the resonance structure for an allylic carbocation, you take those pi bonds and they go toward the positive charge. So that positive charge then goes away, the pi bond moves, and the one carbon that loses electrons in that exchange, that now has that positive charge. So those are your two resonance structures, and after you do that first nucleophilic attack, you have a bromine all by itself. And the bromine now is going to act as a strong electrophile because it's got that negative charge there. So that can attack two places. It could attack the carbocation represented in the resonance structure on the left, and if that happened, then you would get this product, or the bromine can attack the electrophilic center represented on the resonance structure at the right, in which case you would get this product. So those two products are what you'd get if the second pi bond acts as the nucleophile. And if you wanted to classify these, you could see where the hydrogen and the bromine attach right next to each other. That's the 1,2 product. And in the other product, they attach on carbons number 1 and 4. So that's called the 1,4 product. So the four products you'd get if you did this reaction are these four right here. And the mechanism for how you produce those is given over there. The mechanism for this next one isn't quite as drawn out because the molecule is symmetrical. So if it's symmetrical, that means it doesn't matter which of the pi bonds acts as the nucleophile. It amounts to the same thing. But those two pi bonds are nucleophilic centers, and so they are going to attack the slightly positive hydrogen in this hydrogen bromide molecule. The bromine is pretty electronegative, so it becomes slightly negative, and the hydrogen is losing that electron density, so it becomes slightly positive. So those electrophilic pi bonds, doesn't matter which one you choose since the molecule is symmetrical. I'm going to choose the one on the right. That will attack that electrophilic hydrogen. Hydrogen can only form one bond, so if it's going to form this new bond, then the bond that it had has to break. Bromine already had 3 lone pairs. When this bond breaks, the electrons go onto it. It's the most electronegative thing nearby. So it's going to get a 4th lone pair and a full negative charge. And the hydrogen is added to the carbon at the top here, because that gives you an allylic carbocation, a carbocation that's one atom away from an atom in a double bond. So that positive charge is stabilized through resonance, which means we have to warn people, put those brackets there that tell people none of the structures in these brackets ever exists, only the average ever exists. And when you have an allylic positive charge, to draw the other resonance structure, the other one that you want to use to average the structures together, you move that pi bond toward the positive charge. So the pi bond moves, And the positive charge on that one carbon goes away because electrons are there now, but the carbon that the pi bond moved away from, that now has a positive charge. So those are the two resonance structures for what was the diene, for what was the conjugated pi system. So when hydrogen was attacked, bromine left. Bromine left, it had 3 lone pairs already. The 2 electrons in the bond became a 4th lone pair. And so now that has a full negative charge and is able to act as a nucleophile. And that nucleophile can attack either of the slightly positive carbons. It could attack the carbon that seems to have a positive charge in the left, the resonance structure there. And if that happens, then you would get this product. Or the bromine can attack the other electrophilic center, which is that carbon there. And in that case, you would get this product. And so those are the two products you would get from this reaction. Notice in one case, the hydrogen and the bromine are right next to each other. That's the 1,2 product. In the other case, they're on carbons number 1 and 4. So that's the 1,4 product. So these two products, the 1,2 product and the 1,4 product, are the products you get from this reaction. All right, so we'll draw out this mechanism one more time. In this case, it's also going to be a little more straightforward because we have that line of symmetry. And so it doesn't matter which of these pi bonds acts as the nucleophile, it amounts to the same thing since they're symmetrical. So we'll take that molecule and those two pi bonds will act as nucleophiles. And then we have the hydrogen bromide. The bromine there is pretty electronegative, so it pulls electrons to itself, becomes slightly negative, and the hydrogen there becomes slightly positive. So one of these pi bonds goes and attacks the electrophilic hydrogen, the slightly positive hydrogen. Hydrogen can only form one bond, so if it's going to form this new bond, the bond it has to break. Those electrons go onto the bromine. Now that bromine already had 3 lone pairs. The electrons from the bond is going to give it a 4th one. So after that first step, we're going to have this molecule. The hydrogen adds at the end because if it adds there, you get an allylic carbocation. And that carbocation is going to be stabilized through resonance. So that's the most stable carbocation, so that's the one you get. Now, because you have resonance, you have to warn people. You draw the brackets to tell them none of the structures inside are true, ever. The only true structure is the average of the two. And that's what that arrow means, take the average. To draw the resonance structure for that, what you do is you would move the pi bond toward the positive charge. And so if you do that, then the positive charge goes away. It's being stabilized by the electrons there, but the carbon that lost those electrons now has a positive charge. When the hydrogen was attacked, the bromine left, and so now it exists as a bromide ion with a full negative charge. So it's going to act as our nucleophile. It acts as our nucleophile to attack our electrophilic centers. There are 2 of those. It could attack the electrophilic center on the top, in which case we would get this product. Or it could attack the electrophilic center on the bottom. On the bottom. In which case we would get this product. And so if you wanted to classify those products, the ones where the hydrogen and the bromine are right next to each other, that's the 1,2 product, and the other product is the 1,4 product. So you'd end up getting both of those, two products, when you do this addition reaction to the conjugated pi bonds.